All right, so get this. We're diving into something today that's seriously rare.
Oh,
Like 1 in 50,000 rare.
wow. That's,
I know, right? It's like winning the lottery while getting struck by lightning, while finding a four-leaf clover.
uh-huh. Okay, you have my attention.
We're talking about something called the Einstein Zig-Zag. It's the first time we've ever seen a single
And
quasar.
single what?
Quasar. It's appearing 6 times in one single image.
Okay, now that's something I gotta see.
Imagine like a bowling ball on a trampoline. You know how it kind of warps the surface?
Yeah, sure.
So now, replace that bowling ball with a galaxy and the trampoline with space-time. That's the basic idea behind gravitational lensing.
Ah, I see. That's a pretty cool analogy.
Yeah, it is.
So what's really wild is that this warping, like Einstein predicted in his theory of general relativity, it doesn't just mess with stuff that has mass, it bends light itself.
Exactly.
It's mind-blowing.
It is. So in this case, the light from this distant quasar, which is basically a supermassive black hole that's super bright, is getting bent. Yeah, bent around not just one, but 2 galaxies.
2.
Yeah, 2 galaxies that are lined up perfectly, like a cosmic magnifying glass.
That's how we're seeing 6 images of the same quasar then.
Yep,
And it makes this zigzag pattern.
exactly. And get this, this was all discovered thanks to the James Webb Space Telescope.
Oh, the JWST.
And this isn't just some cool picture. This perfect alignment actually helps us tackle some of the biggest mysteries in cosmology.
Oh, really? Like what?
Well, for one, there's this thing called the Hubble tension. It's basically this difference between the predicted expansion rate of the universe and what we're actually observing.
Like we're getting 2 different answers.
Yeah, it's like trying to measure a room and getting 2 totally different lengths depending on which tool you use.
Huh, that's weird.
I know, right? So the big question is, which measurement is right?
Right. That's what we need to figure out.
Exactly. And this Einstein zigzag might actually help.
Wow.
Well, because of its precise alignment, it's like the super accurate cosmic yardstick.
The yardstick.
Yeah. You see, the time delays between when the light from each quasar image arrives, that lets us measure distances and expansion rates super precisely.
Wow.
So it might help us figure out which of those measurements is more accurate or even if we need to totally rethink our understanding of cosmology altogether.
That's huge.
It is, right?
Yeah.
But hold on, there's more. We also have this mysterious thing called dark energy.
Ah, yes, dark energy. The force that's making the universe expand faster and faster.
Right. What can the zigzag tell us about that?
So imagine the universe as this car that's speeding up.
Okay.
Dark energy is like this mystery fuel pushing the gas pedal.
Hmm.
But we have no idea what it's made of or how it works.
We need to figure out its properties, though.
Exactly. There's something called the equation of state for dark energy that we need to crack. And this zigzag lensing system, it gives us a rare chance to do just that.
Okay, so this equation of state, is it like figuring out what kind of fuel powers this dark energy engine?
Precisely. By studying how the light is bent and delayed, we get clues about how matter and dark energy are spread out along its path. And that helps us narrow down the possible values for this equation.
So by knowing this equation, we can predict what dark energy will do. Like, will this cosmic car keep accelerating forever?
Exactly. Will it slow down eventually? Or could it even reverse and cause a big crunch? This equation could tell us.
Wow, okay, this one image is raising a lot of questions.
You could say that. It's pretty amazing.
It's like a cosmic Rosetta Stone.
Right. And to really grasp how big this is, we need to go back a bit. So this quasar system is called J7721 plus 88842. Get this. It was actually spotted back in 2017.
Wait, really?
Yeah.
So what's different now? Why is this zigzag such a big deal all of a sudden?
Well, back then, telescopes weren't as powerful. We could only see 4 images of the quasar.
Ah, I see.
But the James Webb Space Telescope, the JWST, it's got incredible resolution. It's revealed the full 6-image zigzag for the very first time.
It's amazing what better technology can do, huh?
It really is. And we're talking about mind-boggling distances here. The light from the closest galaxy in this system, it's been traveling for 2.3 billion years to reach us.
2.3 billion years. We're seeing that galaxy as it was before dinosaurs even existed?
And the light from the farther galaxy has been traveling for a whopping 10 billion years.
Wow.
And the quasar itself, we're seeing it as it was about 11 billion years ago, just a few billion years after the Big Bang.
We're basically looking back in time to the early universe.
We are. It's pretty amazing, isn't it?
It really makes you realize how small we are in the grand scheme of things.
It does.
And all of this is because of this incredibly rare alignment. What are the odds of finding another Einstein zigzag out there?
Well, the odds might seem tiny, but remember, we've barely scratched the surface of what's out there. The universe is huge.
So there could be more of these zigzags out there just waiting to be discovered.
Exactly. And new sky surveys, like the Vera Rubin Observatory, they're being built specifically to scan the entire sky, looking for rare events like this.
Wow. So the next step is to go on a cosmic treasure hunt and see if we can find more.
You got it.
But before we get into that, I want to know how scientists are using this current discovery. It's one thing to find it, but how do they actually use it to tackle these cosmic mysteries?
That's a great question. It's like the universe has set up this natural experiment for us.
Okay, I like where this is going.
So let's start with that Hubble tension we talked about. Remember, we have those two different ways of measuring the expansion of the universe, and they're giving us different answers.
Yeah, it's like the universe is messing with us.
Right. So one way looks at the early universe using the cosmic microwave background radiation, basically the afterglow of the Big Bang.
Right.
We use that to calculate the expansion rate. The other way looks at objects in the nearby universe. We measure their distances and speeds to figure out how fast they're moving away from us.
And the problem is, these two methods give us different numbers.
Exactly. And that's where Einstein Zig-Zag comes in.
Yeah.
The time delays between those 6 quasar images, they act like a really precise ruler.
A ruler.
Yeah, for the universe. So we can measure distances and expansion rates really accurately with it.
So we can check which of the existing measurements is more accurate.
Exactly. Imagine having 2 tape measures that give you slightly different readings for a table. You'd want to use a more reliable way to measure to see which tape measure is off. That's what this zigzag is doing for us.
Got it. So if the zigzag's measurements line up with the early universe values, then maybe our local universe measurements need adjusting.
Precisely.
But what if it lines up with the local universe values?
Then things get really interesting.
Like how?
It could mean our whole understanding of how the universe evolved, our standard cosmological model, it might need a major rewrite.
Oh.
It could mean there's some new physics happening that we don't even know about yet.
Okay, so this little zigzag could have huge implications.
It really could. Now, let's talk about dark energy again. Remember that equation of state we mentioned?
Yeah, the one that tells us how this mysterious force behaves. It's like trying to figure out the personality of a ghost.
Well, think of it like this. Imagine you've discovered a brand new type of fuel. You need to figure out its properties. Does it burn fast? Does it have a high energy output?
Right.
That's what the equation of state is for dark energy. It tells us how its density changes as the universe expands.
Okay, but how does the zigzag help us with that?
You see, the light from the quasar, it doesn't just bend around those galaxies. It's also affected by how matter and dark energy are distributed along the way.
So by analyzing how that light is distorted, we can learn about the nature of dark energy itself.
Exactly. It's like shining a flashlight through fog. The way the light scatters tells you about how dense the fog is and what it's made of. The Einstein zigzag is our cosmic flashlight.
And the universe is our fog.
Exactly.
Okay, I get it. But this is just one zigzag. It's
Yeah.
one data point. We need more, right? To be really sure about anything.
You're absolutely right. One zigzag, while amazing, isn't enough to rewrite the textbooks. But it's a great start.
So where do we go from here? What's next?
The next step is to find more of these Einstein zigzags. And luckily, we've got new tools that'll help us do just that.
Oh, like what?
Well, there's the Vera Rubin Observatory in Chile. It's being built to scan the whole sky every few nights, looking for changes in weird objects.
It's like a giant time-lapse camera for the universe.
Exactly. And maybe, just maybe, we'll spot another Einstein zigzag in one of those photos.
That would be amazing.
It would. And every new discovery like that, it gives us more data, more clues, and that helps us refine our understanding of dark energy, the expansion of the universe, and who knows, maybe even uncover brand new physics we haven't even thought of yet.
That's what I love about science. It's all about discovering new things and constantly learning.
It really is. This one-chance alignment, this cosmic quirk,
Yeah.
it's opened up this whole new window into the universe.
It's like we stumbled upon a secret passage in a giant library.
And who knows what other incredible things we'll find as we explore those passages.
That's what I'm excited to find out.
Me too. Me too. It really is. It makes you wonder what else is hiding out there.
Right. And this discovery isn't just about pretty pictures. It's actually helping scientists.
Oh, yeah, for sure. This Einstein zigzag, it's like this amazing tool.
A tool.
Yeah. It's like the universe set up this perfect experiment for us.
Okay, I like that. A cosmic experiment.
Exactly. So remember that Hubble tension we talk about? How we have those two ways of measuring the universe's expansion, but they give us different answers.
Yeah, it's like the universe is playing tricks on us.
Right. So one method looks at the early universe using this thing called the cosmic microwave background radiation.
The afterglow of the Big Bang.
Exactly. It's like the faint echo of the Big Bang. We use that to calculate how fast the universe was expanding back then.
Okay.
The other method, it looks at stuff closer to us in the nearby universe. We measure how far away things are and how fast they're moving away from us.
And those two methods, they give us different numbers.
They do, and that's where our Einstein Zig-Zag comes in handy.
Okay.
The time it takes for the light from those 6 quasar images to reach us, those time delays, they act like a really, really precise ruler.
A ruler for the universe.
Yep, it's like a cosmic yardstick. We can use it to measure distances and how fast the universe is expanding with incredible accuracy.
So we can double check which of those two methods is closer to the truth.
Exactly. Think of it this way. You've got 2 tape measures, but they give you slightly different readings for the same thing.
Right.
You'd want to grab a super accurate, super reliable ruler to check which tape measure is wrong, wouldn't you?
Yeah, definitely.
That's what this Einstein Zig-Zag is for us. It's our super reliable ruler for the universe.
Got it. So let's say the zigzag's measurements match up with what we see in the early universe. Then maybe our measurements of the nearby universe need some tweaking.
Right.
But what if? What if the zigzag's measurements match the nearby universe stuff more closely?
Well, then things start to get really interesting.
What do you mean?
It might mean our entire understanding of how the universe evolved, that standard model, it might need a serious overhaul.
Whoa, okay.
It might suggest there are things happening in the universe that we just haven't figured out yet.
Yeah, we're missing something big.
Exactly. So this little zigzag, it could have huge implications for our understanding of the cosmos.
It's amazing how much information we can get from one little image.
It really is. It shows you how powerful observation is in science.
Right. We can't create these cosmic events ourselves. We can only watch and try to understand what they're telling us.
Exactly. And sometimes the most unexpected things can lead to the biggest breakthroughs. Now, what about dark energy? Remember we were talking about that equation of state?
Yeah, that thing that's supposed to tell us how dark energy works. It's like trying to read the mind of a ghost, isn't it?
It's tricky, that's for sure.
Yeah.
So think of it this way. Imagine you've discovered a brand new kind of fuel.
Okay.
You want to know everything about it, right? How it burns, how much energy it releases.
Right.
That's what the equation of state is for dark energy. It tells us how its density changes as the universe keeps expanding.
Okay, so how does this zigzag help us figure that out?
Well, the light from that quasar doesn't just bend around those galaxies. It's also affected by everything it passes through along the way, all the matter and dark energy.
So it's like help. The light is carrying information about dark energy.
Exactly. By analyzing how the light's been distorted, we can get clues about what dark energy is like, how it's spread out in the universe.
Okay.
It's like shining a flashlight through fog, right? The way the light spreads out tells you how thick the fog is, what it's made of.
So the Einstein Zig-Zag is our cosmic flashlight.
You got it. And the universe is our foggy mystery to explore.
This is so cool. But it's just one zigzag, right? Like we were saying before, we need more data to be really sure about all this.
You're absolutely right. One zigzag's amazing, but it's just the beginning.
So what's next? How do we get more data?
Well, the hunt is on for more Einstein zigzags. And the good news is we've got some new tools that are going to help us a lot.
Ooh, like what?
There's this incredible new observatory being built in Chile called the Vera Rubin Observatory. It's going to scan the entire sky every few nights, looking for anything that's changed, anything unusual.
Wow, so it's like a giant time-lapse camera for the whole universe.
Exactly. And who knows, maybe we'll get lucky and spot another Einstein zigzag in one of those images.
That would be incredible.
It would. And every new discovery like that, it gives us more pieces of the puzzle, more clues about dark energy, about how the universe is expanding.
And maybe even some clues about brand new physics we haven't even imagined yet.
Exactly. This is what makes science so exciting, isn't it?
Oh.
Always discovering new things, always learning more.
It's like we're explorers, charting a vast uncharted territory.
We are. And this Einstein zigzag, it's like we stumbled upon a secret path in that uncharted territory, a path that can lead us to incredible discoveries.
I can't wait to see where it leads us next. It really is mind-blowing how this one weird zigzag can change so much of what we thought we knew about the universe.
It shows how important it is to just keep looking, keep observing.
Yeah.
We don't get to set up these cosmic experiments.
Right.
The universe does that for us. We can just observe and try to figure out what it all means.
It's like the universe is talking to us in the secret code,
Yeah,
and we're just starting to crack the code.
exactly. And this Einstein Zig-Zag, it wasn't like scientists were out looking for it specifically.
Yeah.
No, it was a total surprise, a happy accident. We only found it because the James Webb Space Telescope is so powerful.
That makes me wonder, what else is out there that we just haven't seen yet? What other surprises is the universe hiding?
That's the best part about astronomy.
What is?
There's always something new to discover.
Mm-hmm.
And every time we learn something new, we understand the universe and our place in it a little bit better.
It really puts things in perspective, doesn't it?
It does. It makes you feel pretty small.
Yeah.
But it's also inspiring to see how much we've learned.
Yeah, it is. And it's not just about observing. Scientists are using these discoveries to actually push our understanding of physics and cosmology forward.
Absolutely. Like with that Hubble tension we were talking about.
Right.
That's been a big puzzle for scientists for years. Maybe this Einstein Zig-Zag holds the key to solving it.
Or maybe it'll lead us to even more questions.
Either way, it's good for science.
Oh,
Because it makes us challenge what we think we know and come up with better theories.
right. Always testing, always refining.
Exactly. And this discovery also shows how important collaboration is in science.
What do you mean?
This wasn't just one scientist working alone, or even one team. It took researchers from all over the world sharing their knowledge and working together to figure this out.
That's really cool.
It is.
Yeah.
It shows, but even though we have our differences here on Earth, we can still come together and achieve amazing things.
Especially when we're trying to solve big cosmic mysteries.
Exactly. And who knows what the future holds? With new technology, even better telescopes? Who knows what other mind-blowing things we'll find out there?
Maybe we'll find even weirder gravitational lenses.
Maybe.
Or finally figure out what dark energy and dark matter really are.
It's all out there, waiting to be discovered.
So just to recap, we started with this one image, this bizarre zigzag.
A single quasar magnified 6 times by the gravity of 2 perfectly aligned galaxies.
Billions of light years away.
It's a reminder that the universe is full of surprises.
And that there's still so much out there that we don't know.
That's the beauty of it all, isn't
It
it?
really is. Well, that wraps up our deep dive into the Einstein Zig-Zag. Thanks for listening, everyone. We'll catch you on the next one.
See you then.